The two-slit experiment. This is one of the great mysteries of quantum mechanics, quantum physics till this day. Hasn't been really resolved yet. And potentially a Nobel Prize is waiting for the person who can figure out what's happening. So the experiment is actually quite simple. Suppose you have two slits, one up here, one down here. Okay, so in other words, think of like a piece of cardboard and you cut two holes in the cardboard. You get two slits. And then you have like an observation screen directly opposite those two slits. Now, if you were to shoot, let's say, everyday familiar objects like tennis balls at the slits, okay, so you shoot them from here, and the tennis balls can only go through one slit or the other, right? There's no mysteries there. They can only go through one or the other. If they go in between the slits, they'll bounce back. And then what you'll see on the screen is this. So this is basically the result of the experiment. If you were to fire tennis balls one at a time, let's say, at the two slits, you'll get peaks roughly across from each slit. And that's indicating that the tennis ball that's hit here has gone through this slit up here. The tennis ball that's hit here has gone through this slit here. It's called the slit 1, slit 2. There's no mystery there, right? And probably some have gone in between. Some have potentially bounced off the sides of the slits and they've sort of gone in the middle here. That's the classical case. That's what you would expect from everyday experience, everyday macroscopic objects. Macroscopic means very large. Now suppose you were to close one of the slits. Let's close slit 1. You would expect this. Okay, a peak across from slit 2. Okay, and it makes sense because slit 1's been closed, no tennis balls can go through the slit and across onto the screen. So you'd only get one peak behind slit 2. Similarly, if I was to close slit 2 instead, I'd find a peak behind slit 1. And that peak corresponds to a gradual build-up of tennis balls, collective dots. So the case of the tennis balls is the case of particle behavior. So tennis balls are like particles, massive particles, and that's what you'd expect using tennis balls, they're particles. Now suppose you replace the source of tennis balls with a source of waves, okay? So let's say I have a light bulb or a light source. So light is a wave, right? It's got peaks and valleys, okay? So a light wave looks something like this. Okay, think back to junior science. It's got peaks and valleys. Peaks are called crests and valleys are called troughs. Now with light waves, so light coming out from the light bulb, come out like this. And each slit would act as like a new source of light, right? So light would trickle through each slit. I'm going to exaggerate the diagram here. And you get a secondary source of light waves coming from each slit. So you've got a primary source of light waves here, the initial light source, a source of waves. The slits then act as a secondary source of light waves. So you have waves, picture this in your mind, coming out of each slit. The waves will what we call interfere in physics. Interference means peaks and valleys adding and cancelling. Okay, so if I draw it down here, suppose from slit 1 and slit 2, there's a position where the two waves are in sync. In other words, the peaks match and the valleys, the troughs match. You'll get constructive interference. Constructive means add, right? So the wave will have a larger amplitude like this. They will add to give you a wave with a larger amplitude, larger size. Okay, that's an amplitude there. It's called constructive interference. Now there'll be regions where the waves will be out of sync. Just to make sure I draw it properly. Where a peak corresponds to a trough, a crest corresponds to a trough, and similarly and vice versa, a trough will correspond to a crest. And this is what you call destructive interference. Destructive because a peak, okay, a crest and a trough, they cancel out. Okay, and they give you nothing. Okay, think of it as like being 1 and minus 1. So a peak corresponds to 1 plus 1. A valley, a trough corresponds to minus 1. So 1 minus 1, 0. And that goes along the whole wave. So you get cancellation. That's called destructive interference. This happens along the entire region here of where the secondary light waves come out from slit 1 and slit 2. And you will get what's called an interference pattern. This is characteristic of wave-like behavior. An interference pattern looks like this. You have a central peak between the slits. Okay, it gradually dies down like this. Okay, and I should mention it's typically symmetric around the central peak, right? You get peaks and crests and troughs alongside alongside the peak. Okay, on either side of the peak, it's symmetric. So it looks something like this. There's no mysteries here as well. We can do this at home using a light source, slits, and an observation screen. No mysteries here. This was done in around 1801 by Thomas Young, Englishman. So that's wave-like behavior. Similarly, if you were to get water waves, you would see the same effect. Now here's where the mystery comes. Suppose you were to use a source of electrons. An electron source, an electron gun. And suppose you were to fire electrons at these two slits. What would you get? Here's what you would get. You would get the same interference pattern that you see with light waves. Have a think about that. Electrons are particles. Okay, in high school, junior school, we teach you anyway that electrons are point-like entities, point-like objects. Now I'm telling you that an electron is basically a wave. That's the only way to describe it in this case. Electrons are waves if you use this two-slit setup. And so which is it? Is it a particle or is it a wave? And it turns out that it's actually neither. An electron is a particle or a wave, depending on what experiment you use to study it. And that goes for any other particle in the universe. Same thing with protons, neutrons, even light itself. Light's made of photons, particles called photons, given the symbol gamma, Greek symbol gamma. Light's basically a wave. From everyday experience, we see this wave-like behavior, but it's also a particle. Okay, there's what's called single photon detectors. You can actually detect single photons very accurately. But that's not where it ends in terms of weirdness. Check this out. Should have kept that, that's right. Suppose I were to close slit 1. You would get this particle-like behavior. Okay, a peak, corresponding peak opposite slit 2. Similarly, if I was to close slit 2, I would get a peak directly opposite slit 1. Even more mysterious, let me show you something else. Suppose I had a detector. At each slit, keeping an eye on these electrons, what they're doing. If I was to turn on, let's say, if I was to turn on these detectors, let's see this particle-like behavior. Okay, the detectors are counting how many electrons hit each region of the detection screen. So you get particle-like behavior again. But if I turn off the detectors, unplug them from the wall, lo and behold, I would get back this interference pattern that we had originally. So very mysterious indeed. No one knows why. Maybe you who's watching this, potentially one of my students, can figure out what's happening and win a Nobel Prize someday.